Welcome to GIS 105, Lecture 1, How GPS Works. Hello, my name is Rick Rogers, and I'm an adjunct GIS instructor here for Skagit Valley College. In case you're taking this course as a distance ed student, this is what I look like. This first lecture will be an overview of how GPS works. When we're done, you won't know all there is to know about it, but hopefully you'll have a basic understanding of how your GPS unit locates itself, some of its uses, and some of its limitations. Okay? Let's go. GPS and GIS are often used together, and we'll be working with both in this class. GPS is the acronym for Global Positioning System. This is the satellite-based navigation system that your GPS unit utilizes for positioning. GIS stands for Geographic Information System. This is the computer-based system designed to work with geographical data sets. You are all familiar with ArcMap GIS. So let's talk about how GPS works. GPS basically has two parts: a receiving unit on the Earth's surface and the transmitting satellites in Earth orbit. There are 24 working GPS satellites that make up the Global Position System constellation. This constellation is made up of 6 orbital paths. Each path is 11,000 miles above Earth's surface, tilted 55 degrees in relation to the equator, and they are spaced evenly around the globe. Each of these 6 orbital paths has 4 GPS satellites, and these satellites are spaced evenly around their orbits. Each of the satellites make a complete orbit of the Earth in 12 hours. This is how the U.S. civilian GPS constellation is configured anyway. There are also other GPS satellite constellations up there. The take-home message is this: there are enough satellites up there so that no matter where you are or when you try, you should be able to get reception with your GPS receiver. Okay, so we've established that there's enough satellites up there so you can get a signal, and we know that by working together, your receiver and the satellites can get you a position. Think of a positioning as a solution to a problem. Your GPS unit solved the problem by combining what it already knows with what the satellites are telling it. Your GPS already knows its rough location, roughly what time it is, the satellite PRCs, and the exact PRC timing. What the satellites broadcast to your GPS unit is its ID, or which satellite it is, its exact location in space, the exact time, and its PRC. So the satellites are radio broadcasting their PRCs, or pseudo-random code. These PRCs are broadcast continually, and each satellite has its own PRC. All of the PRCs in a GPS constellation are broadcast on the same frequency, but each satellite modulates its broadcast carrier wave in a unique pattern to create a unique signal that your GPS unit can recognize. So your GPS can recognize these unique satellite signals and it will know which satellite it's listening to. But there's more that it can do with the information contained in the PRC. To use the PRC signal in calculations, your GPS unit digitizes it into a series of ones and zeros. Remember the PRC frequency? Here's a digitized PRC against time. Its wavelength frequency of 340 nanoseconds sets a limit on your GPS unit's positioning precision. Standard GPS units are limited by this 340 nanosecond frequency. Increase the frequency and you increase your precision. Military users have GPS units that can make use of a higher PRC frequency and can get more precise positioning information. Okay, let's go back a little. Remember that the satellites are also broadcasting other information embedded within the PRC or the pseudo-random code. The unique PRC codes are recognized by your receiver, so the PRC pattern will identify the satellite that sent it. But there are two other critical pieces of information that the satellites are broadcasting. They're broadcasting their exact locations and the exact time. The exact satellite locations and the exact time. It's critical that the satellites know exactly where they are and exactly what time it is, so they broadcast the correct information. So the satellites have a ground-based support staff of monitoring stations that are watching and ranging the GPS satellites very closely. And as the satellites move overhead, the monitoring stations are listening to the PRCs to see how accurately the satellites are broadcasting where they are and what time it is. If any of the satellites needs a correction, there's one station that can send these corrections to the satellites. This ensures that the PRCs are embedded with the most accurate time and position data. So the GPS satellites are broadcasting very precise and accurate information to your GPS receiver. And your GPS receiver knows the exact PRC timing for every satellite. This means that for every satellite, your GPS receiver knows the exact point in time that an individual PRC pattern should be starting and stopping. It knows that at this exact moment in time, that this part of the PRC should be starting. But what your receiver actually sees is more like this. It expects the PRC pattern to begin here at this exact moment in time, but it's late and it begins here instead. There is a time lag between the expected PRC and the PRC that's just been received. Your GPS then measures this time lag very accurately. Okay, so let's imagine that these are PRCs digitized into ones and zeros, and that each digit space represents 340 nanoseconds. This PRC pattern on the bottom represents the pattern that your GPS unit expects to hear from the satellite. And this pattern on top is what your GPS actually does receive from the satellite. Your GPS unit detects a discrepancy between the expected and the actual PRC patterns, and then measures that time lag to that particular satellite. It can then calculate its distance to that satellite. The PRC signals broadcast to the satellites to your GPS travel at the speed of light. So the distance from you to the satellite, d, is the speed of light, r, times the measured PRC lag time, t. Because the satellites are also broadcasting their exact locations, a measurement to one satellite will narrow down your possible position to the surface of a sphere. If you measured a time lag of 0.064 seconds, then your GPS will know that you are somewhere on the surface of a sphere with a 12,000 mile radius. Now your GPS will lock onto and measure the PRC lag time to a second satellite. Let's imagine that it calculates 11,000 miles to this second satellite. The intersection of these two possible location spheres will create a circle, and you are somewhere on the circumference of this circle. So now let's get a third satellite measurement. The possible location sphere from this third satellite will intersect your circle in two places. So now your GPS unit knows that you are either on one or the other of these red dots. Your GPS unit knows that you can't be in two places at the same time, so it needs to decide which of these possible locations it can discard. So it asks itself some reasonable questions. Does either location seem to be moving more than 1,000 miles per hour? If so, that location can be dismissed. Or, does either location seem to be a half mile or more underground? Well, you can't get GPS signal reception underground, so that location should be discarded. Or, one of the locations may have you more than 10 miles in elevation, and that location could be dismissed. So now your GPS has a pretty good idea of where you are, broadly speaking that is. At this point, with 3 satellite measurements, your GPS can probably locate your position to within the nearest city block. But it can do better than that. It now locks onto a 4th satellite signal and calculates its distance from that. But there's a problem. The possible location sphere from this 4th satellite does not intersect your likely position. This mismatch can be extremely troublesome. Now, after adding data from the 4th satellite measurement, I don't know where I am. It screwed everything up. Or did it? Can we use this mismatch to our advantage? Okay, let's sketch this out again. We have a preliminary location determined by the first 3 satellites we've locked onto. And now we have a 4th satellite here in red. Now let's consider this. First of all the satellites know where they are. And second, all the satellite signals are traveling at the same speed. So the spheres are in the correct place, yet they don't intersect. What's wrong here? The problem is the clocks. This is just a part of the atomic clock that's telling the satellites what time it is. And this is the clock telling your GPS unit what time it is. This one, right here. So maybe if we're going to monkey with the timing a bit, we can get all 4 of the spheres to intersect at one point. And if we're going to monkey with the clock, let's monkey with the clock in your GPS unit. So for this example, let's start turning back your GPS unit's clock. Turning back your GPS unit's clock a certain amount will add a corresponding distance to all of the possible location spheres radii. Let's see if we can get alignment after this clock adjustment. No, not quite yet. Let's turn the clock back a little bit more. Now, we've got an agreement between all the 4 satellites. Your GPS makes a note of the time adjustment it had to make to get this agreement, and then it resets its internal clock accordingly. Now, your $100 GPS unit is just as accurate as the Navy's billion-dollar atomic clock. And you know where you are with a pretty high degree of precision. You may wonder how confident you can be about your location. You know, different applications require different levels of precision. If you're going to drop an H-bomb, you don't need to worry about your precision as much as you would need to if you were using your GPS unit to perform eye surgery. What you can expect is precision about in this range, about plus or minus 10 meters. But are there factors that can improve or degrade your GPS unit's accuracy and precision? Your understanding of these factors will largely determine how well your GPS unit can work for you. Of all the factors that can affect your unit's performance, how cool it looks ranks regrettably dead last. And that's too bad, because I'd love it if we all had to carry these things around. The most important factor that affects your GPS unit's precision is simply where the satellites happen to be above you and how many of them you can get signals from. This is known as the geometric dilution of precision, or GDOP. Let's start with this diagram of satellite positions that would provide you with pretty good precision, or a good GDOP. Note that all the satellites overhead are, from you, roughly 90 degrees apart. The possible location spheres from these satellites will intersect very nearly perpendicularly. Note that the location spheres are drawn as widened lines here. The space between these lines represents the distance that the radio waves can travel in 340 nanoseconds. Remember why? That's the frequency of the PRCs. Your GPS unit's timing precision cannot be greater than this. The gray intersect area shows the range of your possible location. If you're unlucky enough to have satellites in a poor configuration, their spheres will be intersecting at shallower angles. This will result in larger possible position areas and a dilution of your unit's precision because of the geometry of the satellite positions overhead. geometric dilution of precision, GDOP. Getting a good GDOP is especially difficult if you can't get a clear view of the sky. Okay, so there are limits to your GPS unit's precision. How will that affect you? Here's an illustration. Say you put your GPS on a fence post and leave it there for a couple hours. Every few minutes you check to see where your GPS unit thinks it is and log the positions. Imagine also that you had surveyed the area and that you already know exactly the fence post's position. You can then plot the results with the plot center crosshairs representing the fence post's true position. The GPS positions that you log will look sort of like the blue dots on this plot. The green circle is drawn with a 15-meter radius, and with good GDOP, about 95% of the plotted positions will be within this green circle. You can be 95% certain that your GPS unit position is accurate to within plus or minus 15 meters. The red circle is drawn with a 5-meter radius. You could be 50% certain that your GPS accuracy is plus or minus about 5 meters. There are other factors other than GDOT that can affect your GPS unit's precision or accuracy, and I've listed them here. If you want to know more, you can hit Escape to exit this presentation and then click on the error sources listed on this slide for more information. They're hot linked to other online information sources. With a good view of the sky and good batteries, handheld GPS units are pretty reliable. This brings us to the last factor that affects your GPS unit's precision. The GPS user's ability to grasp the fundamentals of GPS positioning, and, yes, that's me again, the user's understanding of the inherent GPS limitations. So here's a diagram of good GDOP again. If you're on flat terrain, the satellites are aligned pretty well for positioning. But if you're not on flat ground, what happens to your precision then? Imagine you're climbing Prusik Peak near Leavenworth with your wife. You're most of the way up and you want to get up here to the summit, but your wife wants to stop here. Well, what do? Well, one thing you could do is find a comfortable place for her to sit, tie her to a rock, and then mark her location with your GPS unit. Finish climbing to the top, and then pick her up on your way down. This diagram represents the search radius you would need to look for your wife with good GDOP. It would be like finding her somewhere in the house, and this is not a problem. But remember that the mountain is blocking a big portion of the sky. So you would have poor GDOP, poor GPS precision, and a larger search radius. This represents the area to search for your wife. This is a little tougher. This is more like trying to find her in Safeway. But that search radius would be projected onto the side of a mountain, not onto a flat surface. Your search area would be oval in shape, about 250 feet wide, and about 450 feet in length. This is more like trying to find her in a Costco superstore. But remember the GPS on the fence post example? In that case, surveyors had already been there and accurately located it for you. In this case, they didn't. So when you logged your wife's location the first time, chances are pretty slim that she was in the center of the search area. She may have been here. That means that when you come back searching for her, still with the same GPS precision, your search area is compounded to here, or here, or here, or here. This is more like looking for her somewhere in the general vicinity of an international airport. Starting a search of this magnitude by yourself at dusk on the side of a mountain could be difficult, and the experience could change you. The experience may also have an effect on your relationship, and these effects may be long-term. So if the blue arrow is representative of common GPS precision, then geocaching your wife on the side of a mountain would be an example of what you could do to lessen that precision. What can you do to strengthen or augment your GPS unit's precision? Well, how much more accurate can you get? Here's a 15-meter circle drawn to scale. Used correctly, you can be 95% confident that your true location is inside this circle with an average GPS unit. DGPS, or differential GPS, is any ground-based system used to boost normal GPS positioning accuracy. WAS is the most widely available system for differential GPS augmentation in the United States, and it's free. WAAS stands for Wide Area Augmentation System. If your GPS is WAS enabled, you can be 95% confident that your true location is inside this green circle. Why the difference? Well, the space between you and the GPS satellites isn't exactly perfect for transmitting radio waves, so those radio waves are bent slightly one way or the other as they make their way through the electrically charged portions of the atmosphere. And the way they are bent isn't uniform either. I mean, once they are bent one way, they don't always stay bent that way. Think of the shimmery bent light waves you see in a mirage. The PRCs from the satellites are tormented in much the same way. So the distances your GPS calculates to each satellite is always a little off one way or another. DGPS, or differential GPS, tries to account for this shimmering, and this is how. Remember the GPS unit you left on the fence post? And remember that the fence post position has been surveyed in precisely and that the positions it logs don't match the surveyed location? Well, now attach a calculator to it so that each time it calculates its GPS position, it can subtract that from its surveyed position. This returns the differential between its GPS position and its true position. Well, now attach a radio transmitter to it and set it to transmitting these differential GPS correction factors in real time. Put another receiving antenna on your GPS unit and you have a DGPS system. The WAS system, or the Wide Area Augmentation System, works pretty much just like that. You can think of the U.S. WAS system as having GPS units on fence posts scattered across the U.S. These send differential corrections from all over the country to master control stations on either coast. All of these differential corrections are beamed from the control stations to two geosynchronous satellites, and these satellites broadcast these differential corrections over a wide area to augment your GPS receiver's position. So, WAS-enabled GPS units can achieve 3-meter accuracy. But can you get even better precision? Well, yes, you can. You should have the idea by now that when it comes to GPS ranging, that time is distance and distance is time. So let's think about the differential correction factors that are being transmitted for WAS. Say you are using a WAS-enabled GPS somewhere in Oklahoma. To get the differential correction signal from your nearest reference station, that signal has to travel about 1,000 miles to a master control station on the coast. From there, that signal goes to a repeater satellite in geosynchronous orbit. So that's another 17,000 miles or so. And then from there, the correction signal has to get back to Earth and your GPS unit. Even at the speed of light, each leg takes time. And the cumulative effect of that, all of your correction factors will be about the cumulative effect is that all of your correction factors will be about 0.2 of a second old by the time your GPS unit can use them. The atmosphere can do a lot of shimmering in 0.2 of a second. Base stations work off the same principle as wide area augmentation, but in a much smaller area. First, you survey in and set up reference stations around the perimeter of your job site. Then you set up your control station in the job site trailer office. The transmission distances are much shorter and your correction factors are near instantaneous. Base station DGPS systems can improve GPS precision to plus or minus a centimeter. Here's an example of a base station system in use. Reference stations and a master control station computer are set up on this job site. In addition, the ground prep blueprints have also been loaded into the master computer. This allows the master computer to control the precise elevations of the GPS receivers on either side of the bulldozer blade. To get a precisely graded surface, the dozer operator keeps his hands off the blade controls. See? No hands. GPS is finding its way into almost every aspect of industry and even of everyday life. The better you can understand how it works, the better you can make use of its capabilities while avoiding its limitations. Okay, thanks for staying with me this long. I know this is a tough way to start. The next lecture deals with some GPS applications for my regular job. Well, thanks for listening and have a great day.